At Limelight, our use case is more about the delivery of the content because generally speaking, if we changed our customers' content, they wouldn't be very happy with that. So we tend to get out of that business and optimize the delivery of that content for various things, for quality as well as also to ensure efficiency and scale. To keep up with the price compression in the CDN industry, you need to get 20–30% more efficient every year just to keep your head above water. And so it's an engineering challenge. And if you think about it, every piece of content is a little different from a cost profile to deliver. It's why when you look at CDNs that let you sign up for services, self-service, there's always a GB fee and a request fee, because those things have fixed costs, and a tiny object costs a lot more to deliver than a bigger object, and if you charge GB for everything, you're going to lose money. So we needed to model that, and we spent a number of years modeling that by hand and saying, well, based on our experiments on a typical server in a lab, a request takes about the same amount of CPU to process as delivering 32 KB worth of data. So we'll just use that as a fudge factor to estimate. But it turns out that in the real world, every server is different. You could have a server with hyper-threading turned off because it's on a legacy CPU that maybe had issues with it. You could have a server in a highly regulated data center in France where you get a noise complaint. You need to slow the fan speed down, so you need to turn off turbo on the processors. You could have a server that is very powerful, but because you are now doing a lot more out of that server than you did when you bought it because of the software engineering gains you've gotten over the years, that server only has dual 10 gig NICs, but it's capable of pushing more than 18. Now the NIC is the bottleneck. So you can see that the problem space expands. There is no such thing as a typical server anymore. In a company with tens or hundreds of thousands of servers, every server might have a different breaking point and might have a different sweet spot. So if you're trying to target the best possible quality, you don't want to push a server to its breaking point. And so to figure out every server's sweet spot, what's the old way of doing it? Get every permutation of every kind of server and put it in a perf lab and load test it. Well, then you're missing another element of the equation, which is that at peak hours in London, we might be doing more Sky, Sports, and home.pt.com website images, but at peak hours in New York, we might be doing a lot more Prime Video than anything else. And now, that's a different traffic mix. The server is going to behave very differently. One server might hit its breaking point or its peak operating point at 38 gigabits per second, and in another market, it might hit it at 22 because it's dealing with smaller objects and non-cacheable objects and more complex rules at the edge. So we applied machine learning to sort of figure out every server's sweet spot. And hopefully I'll get to talk a little bit more about it later, but not just in the moment, but 2 weeks in advance. Because if you make decisions in the moment and reroute traffic to another server, all of a sudden that server is a cache miss and you're disruptive. So the idea is to figure things out in advance, because traditional load balancing techniques of when a server hits a high watermark, drain traffic and put on another, don't work very well in a caching context, because anytime you drain traffic away from server A to server B, you're now exposing server B to new content it's never seen before, and you're putting load on the customer's origin. So ideally, you want to never let server A go past its sweet spot, and you want to try to make that decision days or weeks in advance. And that's how and when we started using machine learning.